Okay, I think we can start. So welcome back, everybody. So this is Kate's third lecture. And go, we're ready when you are.
Okay, all right. I realized when preparing this, I have no hope of getting through all the things I want to do. So I'm afraid I'll probably have to skip a few things, but we'll get as far as we can. So where we were last time, we went through the solar and reactor sector, the 1-2 sector, and I was going through the how we know what we know about oscillations. Actually, I'll turn off the video because it seemed to gum things up before, so let's do it. How we know about the 2-3 mixing angle and delta M squared. So we were in the middle of talking about atmospheric neutrinos, which are GeV scale neutrinos, where you expect well-known flavor and up-down symmetry. And the strategy is to tag the flavor of the neutrino by the flavor of the outgoing lepton, and you know the energy in a detector like Super K from the amount of light, for example, that is produced. And then you know the direction and therefore the baseline by the angle. You can infer the path length from the orientation of the ring that comes from the charged particle, because the charged particle direction, it's not a perfect alignment, but it's relatively well aligned with the incoming neutrino direction. And that alignment actually improves with energy. Okay, so here's, I guess, the first new one. And so here is now, this is the famous plot that was shown in around 1998 from Super K, showing the Zenith angle distribution. So this is the distribution of angles at which the neutrinos rings were seen, where cosine theta, it's actually strictly nadir distribution, but somehow, for some reason, the convention is to call it Zenith, but okay, whatever. What it actually means is that cosine theta of -1, this refers to an upgoing neutrino. Strictly, it's a lepton, which is approximately an upgoing neutrino. Cosine theta of +1 is a downgoing neutrino. And the left-hand distribution here shows electron-like events. So these are the ones that have fuzzy rings. And so the lepton that comes out of the interaction is scattering and showering. And so it's a kind of mushy ring. The right-hand plot here is mu-like events. So these are sharp rings. And in both plots, the blue bars are the expectation. So the blue bars are what you expect if there are no oscillations. And so the blue bars here are no oscillations here. Not just that, but all the blue bars. And you can see you get about as many going up as coming down for the electron-like events. The data points are the actual data points, are the observations. And you can see for the electron-like neutrinos, you have about as many going up as coming down. But for the muon-like events, the ones that are primarily muon neutrinos, although the expectation, the blue bars, is about as many going up as coming down, just from geometric symmetry, what you see is that there's this enormous deficit of nu mu from below. And so this is the too few nu mu problem. And it's a path length. These are the long path length ones. There's a path length and energy dependent deficit. And these events are binned in energy. These particular plots are integrated over quite a lot of bins of energy, but in what we can actually do with the data is bin it in energy and path length and fit that to oscillations. And so this is an example of the fit, and fitting to a two-flavor hypothesis simply, and that actually works reasonably well for the data. Actually, the red lines on these plots, these red lines here, are the best fit to oscillations. This is another way of showing the data here on the left, is plotting as a function of L over E. You can actually see the little wiggly thing here down here. This is an oscillation wiggle. This is if you determine the baseline from the direction, and then you measure the energy from actually how much energy that lepton has. And both of those are imperfect measures of the neutrino energy, but they are something that statistically tell you about the distribution of energies as a function of baseline. And what you see here is a disappearance. So this is a disappearance. And it's consistent with nu mu to nu tau. And nu tau is approximately invisible for atmospheric neutrinos. So why is it invisible? I don't seem to find the chat here. It seems to be lost. Here it is. Anybody want to answer why is nu tau invisible? Why is it a disappearance here? Yeah, there's basically, exactly, that's right. It's below charge current threshold. And so there is actually a little bit of tau. The atmospheric neutrino spectrum is, does poke out into, it's a power law. You get a little bit of high energy stuff. The threshold for producing a tau here is about, in the lab frame, charge current threshold is something like 3.5 GeV. And there's some neutrinos above that threshold. So we actually do have a little bit of a sample that is creating, we do have a tau sample, but it's a small one. Most of the muon neutrinos, if you have an oscillation to nu mu to nu tau, you basically see very little. And so it looks like a disappearance. And what we do, so this is just in a simple two-flavor context. You have, somehow this is, what is this here? Here. Somehow this is the, oh, there it is. Nope. Dismiss. Nope. Somehow the webinar feature. Okay, let me get rid of it here. There. Okay, that's better. And so if you fit in a two-flavor assumption, of course, now we know it's not really two-flavor. If you fit for these two parameters, for the mixing angle, which is the amplitude of the wiggling, and the delta m squared, which is related to the wavelength as a function of energy. We have actually a bunch of energy, so it's not just a single wavelength. There's a bunch of wavelengths. This is the fit that you get. These are the parameters describing the two-flavor oscillation, describing the two-flavor disappearance. And I think it's a 90% confidence level is the red one. And what you see is that it's consistent with maximal mixing. So if sine squared 2 theta is 1, then that's the largest amount of mixing that would correspond to a mu mu turning all the way into nu tau that you'd have at a particular L over E, 100% probability of nu tau. So it's consistent with that. We don't know how far away from that it is even now, whether it's maximal or not. And the delta m squared is something like 2.5 times 10 to the minus 3. So it's a different scale, much larger delta m squared by almost 2 orders of magnitude than the solar one. Okay, and so the next step, so that was atmospheric neutrino oscillations. The first clear signal was in 1998. And then after that was followed by an attempt to tame the source and study oscillations with a human-made artificial atmospheric neutrino beam. And so basically next step here is long baseline beams. Where the simplest way to describe it, what you're trying to do is basically generate neutrinos. If you can generate neutrinos with a GeV scale to get the same L over E, that corresponds to a baseline of something like 100, some hundreds of kilometers. Okay, so that's why it's a long baseline. You got to have at least hundreds of kilometers. And then the idea is you compare the flux and the flavor and the spectrum at near detectors. It's actually possible if you're actually making the beam. You can't do that for atmospheric neutrinos. You can't put neutrino detectors up in the atmosphere. Well, I guess in principle you could, but that would be very challenging technically. But you can do that if you're creating a beam of neutrinos. You can have a near detector and a far detector. And so that's the idea, is you measure at both a near and a far detector. And that actually, if you're measuring the same beam, allows you to cancel some uncertainties that are related to the flux. And you want to design your beam and so here's an example, an oscillation probability as a function of neutrino energy for a fixed L. So if you choose L as 250 kilometers, this is what two-flavor oscillation probability looks like. And you want to design your beam to cover the oscillation peaks. You want to choose energies to cover the region where L over E is such that you would have a large effect from the oscillation. So here you want to design your beam to cover the peaks. You want to pick your neutrino energies such that at a fixed baseline, you get a high oscillation probability, because that's easier statistically to pick out. You can also, if you are constrained to a certain set of energies, that also defines your baseline. So it's really L over E that you're experimentally tuning. Okay, so how do you actually make these tame atmospheric neutrinos? And so you actually do exactly what cosmic rays do in the atmosphere. You accelerate protons. Cosmic rays are coming from space already accelerated. Actually, it's not completely understood how they're accelerated, but they are arriving at us from space. But on Earth, if we want to do it, we have to accelerate them. So you use standard kinds of proton accelerator technology. Then you slam them into a target, which is effectively like the atoms of air in the atmosphere. Then you have a big old magnetic field. This is called a horn, often called a horn, the device that does this. And when you slam the protons in the target, you get a bunch of hadrons, depending on the energy of the proton. Typically, you want to get a lot of pions, so you don't want the energy to be too high. This is something like, these are typically few GeV energies. You get a lot of pions, and you want to focus charged pions forward, such that they are all going in the same direction. Because, of course, you cannot focus neutrinos. Neutrinos don't care at all about anything electromagnetic, and so you can't focus them. However, pions are charged, and so you can focus them so that when they decay, they are boosted forward, and so that the neutrinos are also boosted forward. So you focus these forward. So these pions are the parents of the neutrinos, and so you want to focus the parents forward. So to boost the pions, primarily is pions what you have. And then the pions decay to make neutrinos in a long decay pipe. And so and this will typically be evacuated or have some very light material like helium in it so that the pions are not crashing into things too much. They just decay in flight. And so they decay in flight. And they are boosted forward, and that is what sends the neutrinos off in a beam. Some questions. What kinds of materials are typical for these targets? They're typically, actually they vary, and it depends on what you want. So aluminum, I think, is a common one. There's also titanium has been used. There's some that actually, if you want to stop the pions, that's a different kind of beam. You want something heavy like mercury is actually what you have for that. If you want to stop the pions, if you want them to decay in a pipe, you want a light material. So it's materials like carbon and aluminum, I think, have been used for these experiments. How good is the focusing angle? Do we not lose most of the flux with the detectors very far? That is absolutely right. We do lose a lot of flux. You want to focus it as well as possible. And that is actually kind of the whole life of people who design the beams, is to try to design the magnetic horns and design the beam pipe geometry and everything to optimize the amount of neutrinos at a far destination, and also, not lose as little as possible. Also, you want to get the right energy, and that's actually not that easy. You often you want to have some, the distribution of energies may be very broad. You often want it to be very narrow. There's actually a trick to make it narrow, is if you go off beam axis, it turns out that the you can, just by the kinematic decay of the pun, you can actually narrow the spectrum. And so it's a whole subfield is trying to optimize the neutrino production in a beam at a far detector. But it's absolutely right. It goes as 1/r². You're beaming forward, but for example, at the super K detector from the T to K beam, which I'm going to talk about, the beam is many, many kilometers wide. And that actually, in some ways, is a good thing in the sense that you don't have to aim it all that. If it's not a pencil beam, the aiming, I mean, of course, you have to aim it well enough, but it can be very flat over a big center of the beam. And so it's, it doesn't have to be super, super precisely aimed because the far detector is going to be sitting in the middle of the beam. But yeah, these are all very challenging technical questions. Okay, so that's how you make them. And so here are some beam experiments. The first one was K2K. That was a beam from KK to Kamioka to Super K. So the same Super K detector was used. So that was the first generation beam. This is kind of the recent past and current generation beams. So there's Minos, which is a beam generated at Fermilab that went to the Sudan mine in Minnesota. That was 730 kilometers. And the power of the beam, so I put down some powers here. That's basically the power of the beam is proportional to the number of protons, which is proportional to the number of neutrinos. And so the higher the power, the better, the more neutrinos you have. And that's also a technical challenge, is to create a beam that is very high power. You want lots and lots of protons, and that comes with a lot of technical problems. You don't want to, you irradiate things, you make things radioactive. You have to dissipate heat. High power beams will be very cause a lot of just heat things up, and you have to there's a lot of technical challenges there. Okay, and so the next that's the recent past generation is Minos, and there was the beam CNGS, CERN to Gran Sasso. I think that's not running anymore. Those were 400 kilowatt class. And then the current generation is, oops, I haven't changed it here. I'm just going to show you that. There you go. So yeah, Minos and CNGS. Then there is Nova, which is running now, and that's actually an off-axis beam. There, it's a slightly narrower beam because it's off-axis, and it's so actually both of these are off-axis. And you lose a bit of flux, but you get a narrower beam close to where the energy that you're interested in, because there's a lot of oscillation. That's where that is. And so Nova is running now. That's up to 700 kilowatts or so, 800 kilometers, a different site in Minnesota. And then T2K is a new beam from J Park, which is close to Tokyo, but it's not the same location as KK. And 300 kilometers to Super K, again, the far detector Super K, and it's a similar power class of beam. Okay, and I'll say just a few things. I won't write too muon here. Muon neutrino disappearance, that was kind of the first achievement of long baseline beams, was to confirm that neutrinos are disappearing in the same way as atmospheric neutrinos, and indeed that was the case. K2K was the first one that did that. And here's just some examples just to what to eyeball on these plots here. They might look complicated, but really they're just showing, most of them have some kind of solid line showing, so like this one here, this red line, solid line there is the expectation with no oscillations. The data you can see is clearly reduced. There's a deficit, and it's an energy dependent deficit, which is consistent with disappearance. This one here, T2K beam, same thing. You can see the solid line is here. This is no oscillations. The data are clearly, oscillations have chomped it away in an energy dependent way. In fact, I think this bottom here is the ratio, and you can see a clear energy dependent deficit. Here, same deal. Okay, this is Nova in the US. It's the same kind of deficit. I don't know if you can read that ratio. So it's basically the ratio of the observed to the no oscillation expectation. So there's clear deficit. And here, this is the interpretation in terms of oscillation parameters. two flavor disappearance. And basically, we have a picture now where all beam, and actually these experiments can look at atmospheric neutrinos, point to consistent parameters. It's actually really lots of data worldwide. And I can mention also, there has been clear observation of taus. We actually know for sure that it's nu mu to nu tau. It's not just an unknown disappearance. There's enough tau appearance. It's a small amount of tau appearance, but there's enough tau appearance actually both from atmospheric neutrinos and also from the beam for CNGS to be clear that it's really tau appearance. Question, so do we have to take into account matter effects in nova and MINOS? I think there are some, but I think it's quite small. And I think it would be even smaller for T decay. I know the effects in T decay are very, very small. But yes, there are. It is a long enough baseline that there is a matter effect to take into account. And in fact, that allows the NOVA with a long baseline to actually have a reasonably good sensitivity to mass ordering, because that is hinges on matter effect. I hope I will get to that by the end of today. Okay, and so next thing. Now we're in the middle. So this is the twist in the middle. This is theta 1,3 is responsible for that middle Euler rotation, complex one, which makes it the geometric analogy not quite right, but it's still kind of a little twist in the middle here. And this is a three flavor context, going back into the three flavor context. And before about 2011, theta 1,3 was known to be small. So something known to cause effects at less than the 10% level or so. So, something, less than around the 10% effect. And that was known from a reactor experiment called SHOW. And there was a huge effort in the early 2000s to go after theta 1,3. And there's really two kinds of strategies to do that. There's beams and there's burns. And so, which sounds very violent, but that's how it's done. There are beams. You can look for appearance in a beam. So there's effects from a non-zero theta 1,3 in the three flavor context that give you a little tiny appearance. So it's maybe 10-ish, some 5-ish to 10-ish% level effect modulation that would give you a little bit of extra nu E popping out of a beam of nu mu on a long baseline beam scale. So basically the strategy here is you look for an appearance. So this is an appearance strategy of GeV scale nu E in a nu mu beam. Okay, so a non-zero theta 1,3 will give you a little bit of appearance. And so here, this is an oscillation probability. This is a nu mu to nu E probability here as a function of neutrino energy for an assumed theta 1,3 parameter. And this is just to illustrate the principle. And for 2-3 parameters that are known. And you can see this is a 7% appearance probability. So that gives you the scale of it. And there were several experiments. K2K looked, it didn't have enough statistics. MINOS also looked. And T2K and NOVA were the eventual experiments that were able to observe this oscillation consistent with a non-zero theta 1,3. Then there's the reactor approach. And here this is a disappearance approach. So reactors pump out lots and lots and lots of nu E bar. And here the idea is to look for a disappearance of few MeV. So that's the energy scale of the nu E bar that come out of reactors from fission on a kilometer scale. And this plot here is showing you, this is the oscillation probability as a function of baseline distance from the reactor. And here you can see the effect of theta 1,3. You get a deficit. It's also at less than the 10% level. This is a small effect at a baseline of a few kilometers. And there were, SHO was the first reactor experiment that tried to do that and actually came up with something consistent with nothing, with 0, but it didn't have great statistics. Then there was double SHO, which was a follow-on with more detectors. Then Diabei, still running, in China, several detectors, and Reno in Korea. And so there's a range of experiments going after that. And so here, these are the data from these experiments. So on the left, we have T decay and nova. This is the electron night-like. So what these detectors are looking for, T decay and nova, they're looking for, or T decay being a Cherenkov detector, super K is looking for some extra fuzzy rings to pop out of a new mu beam. And nova is actually, the detector is a tracker. They're looking for electron-like events to pop out of the beam. And that was actually observed. And then on the right-hand side, here's the data from 3 different reactor experiments. There is, you can see here, this is a disappearance. And so what's shown there is the ratio of the observed spectrum as a function of energy, the ratio of the observed spectrum to the no oscillation expectation. And there's actually, I think that's near versus far. There's actually, these have multiple detectors. Yeah, it's far to near kind of ratios. And so here, I can mention here there's near and far detectors. So nearby, there shouldn't be much oscillation. So if you're here, you don't get a lot of oscillation. But if you're right here, you will get a deficit. And that is exactly what these detectors have observed. And Diabei actually had multiple detectors. Reno, I think was 2. Could be wrong about that. And double SHO also 2. And they observed this disappearance with characteristic near-far spectral distortion. And actually now this is really in fact, one of the I think it's the most precisely known mixing angle with some really high quality data from these reactor experiments, especially Diabei. Okay, and so now we're in a point where we have lots and lots of different experiments, lots of different oscillation channels. So 2-flavor is passé. That's a pretty good approximation. That was a good approximation for atmospheric neutrinos. It was a good approximation for the first beam experiments and first reactor experiments. But now it's all about throwing all the information into a big pot and fitting it all, and really joint fits to multiple oscillation channels is the thing to do. And in fact, even in a single experiment like T decay, we do joint fits to multiple channels, not just a single set of data. It's really, there's multiple oscillation effects. So this is how we now extract the information. So it's neutrinos and antineutrinos of all flavors, E and mu, and in some cases, there's some tau information. Okay, and so here there's also global fits are popular. There's actually several examples in the literature of groups of phenomenologists who work on fitting all the available data, and generally there's pretty good agreement to the output. So really what the output of this is that 3-flavor fits, the 3-flavor fit picture pretty much fits almost all the data. I'm going to come back at the end if I have time to a little bit of anomalous stuff that's out there. But generally all the data fits well to a 3-flavor picture. So this is an example of relatively recent 3-flavor fit to all of the oscillation data that's out there. It might not have the very most latest thing, I'm not sure. But these are examples. These are all the oscillation parameters from the PMNS matrix. And these are the 3 sigma ranges and the answer plus or minus 1 sigma. And under the assumption here, this is normal ordering assumption and inverted ordering. This is what the ordering is still the unknown. And so what do we not know? And so these are the highlighted here in the colors are the really, we know so much now. Of course, you always want to make things more precise, but we know a lot now about this picture, but there are some still things that are not quite perfectly known in this paradigm, in this picture. And one of them here is the so-called octant. And this is, so this is the answer for the 2-3 mixing angle, so the atmospheric and beam one. Is it greater than or less than 45 degrees? And we don't know that because it's consistent with maximal. And of course, if it's exactly maximal, it's not meaningful to say what the octant is. And so it might be very, very close to maximal, but we don't know whether it's greater or smaller than 45 degrees. So that's an experimental question that we don't know. Somebody asked about that, I think, yesterday, and we don't. We are still going after that. It may be answerable. So for CP violation, we now have a little bit of knowledge. We still have weak knowledge. I'll come to the recent TDK result in a little bit, but we don't know very much about CP violation. And then we don't know the sign of delta m squared of the so-called mass hierarchy delta m squared. I guess it's the convention this one uses is 3L. We don't know if it's too heavy and one light, that's the so-called inverted, or too light and one heavy. Okay, and so the that is still an unknown. The data now weakly favor normal, but it's very much not ruled out that it could be inverted. Okay, and this is the next thing to go after, which is this mass ordering. Of course, everything we go after simultaneously, but we don't know whether we have really two big tomatoes and a small one, or one big tomato and two small ones. And I think I mentioned this before. I am going to say mass ordering because some people yell at you if you say mass hierarchy, because we don't know if all of these masses are, there's really they're all above zero by a greater amount than their difference, then they're quasi-degenerate. And then hierarchy is not quite the right word, but okay, whatever. I will sometimes slip and say hierarchy. Okay, and so there's many ways to determine it. They are all hard. Some of them are potentially cleaner than others, and so I won't go into detail of all of them just because I don't have the time. Oh, question. Why is chi-squared equal 9.3 for IH? Where is that from? Is that from this? Where are you getting that from?
That was on your table, I believe, at the top.
Oh. I don't see it.
The delta chi-squared for the inverted
delta
ordering.
chi-squared of 9.3. Good question. I would have to go back to that reference. I would guess that means I would guess that means that that's the best. Okay, yeah, good question.
So I think I know very quickly. So,
yeah.
So the normal ordering is preferred over the inverted ordering?
Oh, this here is the best fit, and this is
so that's how much it changes from that.
Okay, yes, and that backs up what I had said, that there's a mild preference for the normal ordering from all of the data. Yes. Okay. Thanks, Andre. And there's another question: quasi-degenerate scenarios unfavored by cosmology. I don't know if that's completely true. Maybe mildly disfavored. I think it might depend on which cosmology fit you subscribe to, but as far as I understand, it's not. It's not ruled out. Constrained on the sum of the masses. Yeah, it's not. It's on the fit table. Does it mean that IH is disfavored? And yeah, I think the answer is it's mildly disfavored. It's certainly too strong to say IH is ruled out. It's the data like normal ordering a bit better. Okay. Yeah, I mean, the constraint on the sum of the masses from cosmology is something like 0.4 or something, in which case I think you could still call it quasi-degenerate. I think that's not, it's not really disfavored. Okay, so now let me talk experimentally about how we get at the mass ordering. And so one way, and this is really the cleanest way, is with long baseline beams. And I will say a little bit more about that. And so examples are Hyper-K, Dune. There's also information still to be had from atmospherics. And in fact, all the existing detectors will be able to go after it. Also Ice Cube. I won't say too much more about that, but at the South Pole has good sensitivity to atmospheric flux. KM3net is another very large such detector. INO is another one. So there's actually plenty of possibilities there. Reactors, there's one experiment called Juno. I also won't have too much time to go into that, but there the idea is to look in detail at the wiggling of the neutrinos reactors at something like 50 or 60 kilometers or so, where there are very subtle differences in the phase of the spectrum based on the hierarchy. And that is potentially observable. That's very challenging, but it's maybe possible to go to actually succeed there and get information on hierarchy. This is kind of my personal favorite, but it is also likely challenging due to model dependence, but there's also likely signatures in supernova flux of mass ordering. And I won't have time to talk about that, even though I personally like it. So I will say a little bit more about long baseline beams. And this is really, at least in the three flavor picture, there's are difficulties sometimes if you introduce new physics, new interactions and so on. But this is really guaranteed in the three flavor picture with sufficient exposure at long baseline, which looks feasible to determine the ordering. It's really potentially a very clean signature. Okay, and so maybe and it's tangled with CP. I'll say a little. Okay, let me say a little bit about CP violation. And so it's guaranteed here, but the signature, the observable, is tangled with CP violation as well, with the CP with CP delta. And so just to show that, so here's the oscillation probability for three flavors that you showed, that I saw, that you've seen before, I think at least once, probably from Alex's talk as well. And just to show how CP violation comes in, so from this expression, if you eyeball this expression, the probability of transition from flavor G to flavor F is, for a given U, is the same if you take the complex conjugate of the mixing matrix, as you have to UG for a complex conjugate. Okay, you can get that from that oscillation expression. CPT, which we all assume holds, tells you that this is true, that the transition probability of nu F bar to nu G bar is the same as nu F to nu G. Okay, so that's a consequence of CPT violation. If you put these together, take these two things and you put them together, then this should hold. Okay, and so what this is saying is that the probability of transition for nus, for antineutrinos, is the same as for neutrinos with a complex conjugated matrix, okay? And so if U is complex, the second term, this one here, has the opposite sign for anti-news. And the probabilities will differ for news and antineutrinos, for neutrinos and antineutrinos. And so what this is telling you is that observation, if you observe the probability of nu F bar to nu G bar being different from the probability of transition of nu F to nu G, then this is a signature of intrinsic CP violation. Basically a complex U matrix. Let's use that in here. And so this is really the signature CP violation, is if this is what we're looking for CP violation, is, this is the handle, the observable handle we have is looking at transition probabilities for neutrinos and antineutrinos, and comparing them will give us information. But the probability, and I said that mass ordering signatures are mixed up with CP violation. The issue is that matter is not CP invariant in the sense that there's neutrino, the Earth has electrons in it and not positrons. The Earth is matter and not antimatter. And so the problem there is that if you have a matter potential, if you have matter effects, you talked about a little bit, if you have, for example, nu mu to nu e, there's an extra potential. So matter is matter. It's not antimatter. It's electrons and protons, not and neutrons, not positrons and antiprotons and antineutrons. That the matter potential here, you get this depending on the that goes into a matter effect calculation, depends on the electron density here, and you get a plus for neutrinos, and you get a minus for antineutrinos. And so when you work out the whole oscillation probability, you actually get a matter-induced CP asymmetry. Did I make a right-o here? In the second line, from CPT, do you mean P bar nu F to nu G? Oh, yes, thank you. I think I made a typo. It's G to F, yeah, thank you. Great, right-o. CPT, you want to have the T in there as well. Oops, nope, I erased the wrong thing here. Okay, so this is, yes, this is G to F. And then thing that I erased here, what did I just erase? Was F to G. Yep, okay, thank you. All right. Okay, and so here we've got a matter-induced CP asymmetry that competes with the intrinsic one, the one that's driven by the complex phase in the PMS matrix. And so the whole thing is a bit of a big mess. So this plot here is an example showing a CP asymmetry. If you define it as the probability transition for neutrinos minus that probability for antineutrinos over their sum, that's this is a way of quantifying the symmetry. If you plot that as a function of baseline here, even with delta equals 0, even if you have 0 intrinsic PMNS CP asymmetry, you still have a matter-induced one. And so the trick is to disentangle the matter-induced and the CP asymmetry. And so that's the game that we're playing. And so here, this is just an example showing and I wasn't going to try to write this all out because I would really make lots of typos, but this is the probability for neutrinos and antineutrinos, where you have different plus or minus depending on neutrinos or antineutrinos. You change the sign for antineutrinos. And the game, the experimental game, is to measure nu mu to nu e and nu mu bar to nu e bar. And through matter, where in principle you know what the matter density is, and that matter density here shows up here. It's this A that shows up in various places. And fit the heck out of it, gather as much information as you can as a function of energy and baseline, and throw in all the information you have and try to extract the information that you have. And this is hard, but it's doable. And we are now in an era, so this is our current generation of experiments. This current generation has made strides in playing this game. Let me just pause to say a little bit more about it. I won't say too much more, but there's T2K, which is 300 kilometers. It's a high intensity beam, 750 kilowatt class from it's nu mu beam from JPark to Super K. And let me just make a couple of comments here. I guess I'm going to run out of time, so I won't say too much here. But basically, Super K is soon to be refurbished, and this has been delayed now by a few months due to COVID. But it's gadolinium is being added to the tank. The point of gadolinium is actually to tag neutrons. So, for example, if you have this kind of interaction, this is really now going back to the low energy stuff. This neutron here gets captured on a gadolinium nucleus, which then is de-excited and spits out a bunch of gamma rays, which can then be observed by their Compton scatter. And this adds up to about 8 MeV. This is, we had the question about the 2.2 MeV gamma. This is much more visible. This allows tagging of nu e bars, and in fact can help long baseline as well. And this should be happening this year. It's been delayed. We don't know how much more longer, but that is a potential improvement for high energy as well. Okay, and T2K has, this is now information in neutrinos and antineutrinos in both appearance and in disappearance. This is the samples of the data. Here, appearance, you get extra electron neutrinos, so extra rings popping out from the beam. And also disappearance, you also get a chomped out oscillation deficits in the spectrum, both for neutrinos and antineutrinos. You can change the beam to be more neutrinos or antineutrinos. And this is the T2K using all the data. This is a fit of all the data. This is a recent result from T2K where fitting both the mass ordering and the CP delta. And so here, the plot here now and fitting all the parameters. So this is a joint fit to all T2K data. And the top one shows, so the horizontal axis in both cases is the delta CP. So it's fitting that big horrible expression to all the parameters. The top one here, this is sine squared theta 1,3. And if you throw in also the reactor data, you get a much tighter constraint. So inside this region is, I think this is a 1 sigma region, or 68% region. Under normal ordering assumption, this here is the purple is including the reactor data if you throw that in as well, and so that gives a much better constraint there. And you see it constrains also here the CP delta. This one here now is sine squared theta 2,3. So that is very sensitive to the disappearance as well. And here, this is the one parameter. This is marginalized. If you just focus in on what the constraints are for CP delta, this just skims the 0. And so this at 3 sigma. And this one here is normal ordering. This is this bar here, I believe, is the 1 sigma. You can see there's no even 1 sigma region for the inverted. Inverted is slightly disfavored. And so CP delta equals 0 is disfavored at 3 sigma, just barely disfavored at 3 sigma. And the normal ordering is preferred. Okay. Of all of the information that is available. And so that is from T to K. There's also NOVA, which is in the US, which has a different kind of detector. It's a 14 kiloton scintillating tracker. And it's at 810 kilometers of baseline in the US, in Minnesota. And so here are the NOVA appearance and disappearance plots. And so there they're looking, instead of a ring, they're trackers. And so it's looking for a fuzzy track for electrons, something that looks like a shower in the scintillator tracker. Muons are long, sharp lines, tracks. And these are the corresponding plots for neutrinos and antineutrinos. Also, that beam can do neutrinos and antineutrinos for appearance and for disappearance. And this is also something that collaboration can throw into a big old fit. And these are the results of that big old fit. And basically, it's less stringent than the current best T to K, but it also favors delta CP of 3 pi over 2, minus pi over 2. So these are favored. And so all values are still allowed at 1.1 sigma. For normal ordering, and the inverted ordering is disfavored at 1.9 sigma. Okay. And here's just some more NOVA fit results. This is also addressing the octant. The lower octant is a little bit disfavored, but it's not really very, it's not very strong. So lower octant is disfavored, slightly disfavored. And what is happening now is that NOVA and T to K are starting to work together, and it should be possible in the next few years to there's more data being taken. These results will all improve, but there's actually more insight to be had by combining. And so the collaborations are actually having joint workshops now. So joint T to K NOVA is underway. Okay. And in fact, I even have that there. Okay. Okay. And so now for the future. So everything is now in a 3-flavor context. There's actually now more experiments, bigger, better experiments underway. There's the 2 big ones are LBNF Dune and HyperK. So Dune you surely know about. This is the big next big US-based international particle physics project. It is a very large-scale endeavor. The baseline is 1,300 kilometers from Fermilab to South Dakota. It's a 1.2 megawatt beam. The idea is to have a 40 kiloton fiducial liquid argon tracking TPC detector. Also many other topics, not just long baseline beams. One of my favorite things, supernova, proton decay, lots of other beyond the standard model searches. There's a near detector with lots of exciting physics, atmospheric neutrinos, so lots and lots of things. This is what the detector is going to look like, and 4 modules of 10 kilotons each, total of 70 kilotons of liquid argon. And this is, if you're an experimentalist, this is very, very attractive to have very fine-grained tracking. So basically, fine-grained tracking, there's actually different designs for the TPC, which I won't zoom into the details of, and there may be multiple different kinds of TPCs. And this is, many very interesting and challenging experimental problems to solve for reconstruction. This is projection. This is the same kind of plots I showed you before for 7 years of running for neutrinos and for antineutrinos. So you'd see an excess. So this is what it looks like now. This is what an electron neutrino looks like in Dune. You can really do very intrinsically precise tracking. So until an electron neutrino apart from a muon neutrino, and at 1,300 kilometers, it's a very quite dramatic effects that tell you what the hierarchy is. The ordering would be, and so here's some examples for some assumptions. You get a really large excess here. The colored parts are different kinds of backgrounds for electron neutrinos. You can see would be very clean signal. Is all the non-colored parts is the signal. This is you can see also the oscillation sculpted nu mu and nu mu bar, and throwing all this information in. Here's some plots summarizing what the kind of sensitivity would be. And so here, this is as a function of delta CP. This is what the sensitivity would be, the number of sigmas. And here, around here is actually where the favored, currently favored value of delta CP is. Mass ordering sensitivity would be really very good in on a relatively short time scale. Here's just another way of quantifying that. This is as a function of time, what the sigma would be for CP delta for determining that there's non-zero CP violation. And this is for mass ordering. And so if you want to get to 5 sigma, it would be very quick in principle for mass ordering, depending on what the other parameters are. So this one, the red is if the CP delta truth is minus pi over 2, which is what it looks like. It would be a year to determine the mass ordering at 5 sigma. So it's really, really very good capability there. There's also HyperK, which is the corresponding project in Japan. The idea is 317 kilotons of fiducial in 2 different tanks. Each one would be half, and a beam, the same beam, or an upgraded beam, in fact, from J-Park. And there's also some discussion of a second detector in Korea. I don't know what the status of that is, but there's also many other physics topics. So also proton decay, supernova, so many diverse topics. Solar neutrinos, all kinds of things. Multi-purpose detector in both cases. This is a similar plot for 10 years of HyperK. This is a delta CP sensitivity for different assumptions, where the dashed line are so the different dashed or dotted are normal and inverted. This is using a combination here. The best sensitivity is for a combination of atmospheric and beam, and you can see the breakdown. I guess the turquoise there is if we're using atmospheric neutrinos, where you get a huge statistics in HyperK, and then the blue is for beam, and then the red is for combining them. So really also very good sensitivity. Okay, and then beyond, I guess I probably don't have too much time to say anything about that, but there's also ideas for other possible facilities in the farther future, neutrino factories and so on. Okay, I guess I'll use the last little bit of time to just say something very briefly about some of the slightly creepy things that are out there in the data. There are some slightly uncomfortable data that don't really fit this lovely, neat and tidy 3-flavor paradigm. And so I'm going to open this parenthesis. I'm not going to go through all the details of all of these in here, but there are several data sets out there that are somewhat anomalous. And maybe the most famous one is the Lsd experiment at Los Alamos. This was a 30 MeV baseline with, or 30 meter baseline with 30 MeV neutrinos, where there was an appearance of nu mu bar to nu e bar with a apparent delta m squared of about 1 eV squared, which is much larger than the other delta m squareds. And so that is pretty weird and mathematically inconsistent with 3 neutrinos, 3 neutrino masses. You can't have the other 2 delta m squared scales and a big one, so something is not right there. You'd have to have more neutrinos for that to be true. Then there's mini Boon at Fermilab, which was designed to test LSND with a higher L and a higher E, so similar L over E, but both of them changed, and so completely different systematics. And so unfortunately, it actually generated more anomalies. It was not able to really, some answers that are sort of consistent with the LSNE, but not really statistically strongly, and also some other slightly weird excesses at low energy where you wouldn't expect an oscillation. And so it's all a little bit strange, not kind of uncomfortable, not really fitting everything. There's some other things. There's also some possible disappearances, deficits of reactor neutrinos from early experiments, and some early and current experiments, and some. There was also a neutrino radioactive source in the Gran Sasso GNO gallium experiment, which had a bit lower observed event rate than expected. Not statistically that strong. These things are all kind of 3 sigma-ish, not really very, very clean. And one of the favorite explanations is sterile neutrinos. Have extra families, extra types of neutrinos that don't have regular weak interactions. And there is theoretical motivation for this. You may have heard this in some of your other lectures. There's possible reasons that might be helpful in certain astrophysical concepts, in supernovae, for example. However, the cosmology data is not very happy with it. I think it's not completely inconsistent. It's really, it's not completely impossible to have 4 degrees of freedom, but 3 makes it much happier. There could be something else going on, and so this is all a little bit weird. There's a lot of activity in trying to definitively answer these questions, and there are experiments with beams. I'll say a little bit more about that. Especially, I feel like the micro Boon experiment is designed to look at some of these anomalies. Experiments with reactors, actually quite an array of those experiments, and experiments with radioactive sources. Actually, the one that I showed there is, I think, not actually happening, but lots of interesting ideas for trying to test the presence of sterile neutrinos. They're ongoing. There have been some new data, which is also a little bit not clean and weird, but maybe possibly pointing to some possible wiggling in a nu e bar disappearance spectra. So there's Prospect, which doesn't really see anything in a lithium-loaded scintillator. And then other DANCE and NEOS are 2 other reactor experiments which do have potential observed wiggling. And so I think this is really at a stage where it's more data are needed. It's really, that is the one thing to conclude so far, is that there needs to be more data. If you try to fit all the data, it's also still kind of uncomfortable. There are, if you try to fit it to some model of multiple, add in extra degrees of sterile neutrinos, it's still not quite fitting. So some of the data are probably wrong or misinterpreted, or there's something that we haven't thought about yet. And so this is, I would say, parenthesis is not closed. I'm not going to close it because it's still too weird. Okay. I will say a little bit about this. The short baseline program at Fermilab is a liquid argon TC, time projection chamber detector program. And there's the microboon existing detector. There's a new one called SVND, and then Icarus. And these are recently or very soon to be running. If microboon is already running, Icarus is to turn on very soon. So these are really starting to get there. There's some new data coming. These are actually also very exciting detectors if you're an experimentalist working on liquid argon detectors, because there's it's kind of an excellent experience in learning how to get physics information out of these detectors. So the possible futures here, I could say a lot more about sterile neutrinos, but I'm I think soon out of time. Is, if some of these anomalies are confirmed, and even one of them is confirmed, it could be something very interesting. There could be some whole new physics world to explore. It could be that they all go away, and then we just have to keep working on the three flavor paradigm and keep pushing their, measuring things more precisely. So I think that's where we are. So we don't know the answers yet. So here's the overall summary. Now this is a screenshot that I made in about 2011, and it's maybe, I don't know if it's sad or not sad that I haven't changed it since 2011. This is my to-do list on my first smartphone, and we have ticked off Theta 1-3. So that is good news. That was already some time ago. However, all of these other things that are out there, we still don't have any questions. Still don't have answers for. So in the three flavor context, I think we're getting there. So I think we're now here. We're in the sort of two flavor and getting to the 3 sigma range, maybe more than that in the next 5 years or so. I think that's I'll be able to tick those off maybe at some point. I don't know how many sigmas you decide before you have to tick it off. I think to get greater than 5 sigma really is going to need Dune and Hyper K, and so that's going to be some time away. We will have more to come. So you'll probably hear about this in another lecture if you haven't heard already. We're eagerly awaiting more results from Katrin. Here, I think you also heard about this in another lecture. We have to hope that neutrinoless double beta decay will help us here. Somebody asked me, are there other prospects? And unfortunately, I don't know of anything. But of course, here is what we're all hoping for, is that there may be surprises out there. And so I think maybe I will wrap up there and ask people if there's any questions.
All right, thank you. So if there are any questions, you can type them up in the chat. There's one.
Some people seem to use the term sterile neutrino to mean right-handed neutrinos, where others seem to mean extra generations of neutrinos. Is there standard terminology among neutrino experimentalists? Speaking as an experimentalist, I would say I think of it to mean any kind of neutrino that doesn't have regular weak interactions. So I guess it could be either of those things. I don't know if, maybe different theorists have different usages, but I just think of it as anything that doesn't have a so-called active neutrino is one that has regular weak interactions, but one that doesn't have such interactions.
So any other last-minute questions?
Would a positive outcome for NLDBD give information about absolute mass? Yeah, so the information is, yes, some information. It's the observable of the event rate of neutrinoless double beta decay is an effective mass that is absolute masses all folded up with the mixing matrix elements. So at some level, there's mass information in there, but it's not directly. M beta beta. Yeah, it's an effective mass. What do I personally think about the current inconsistencies in LSD, microboon, mini boon, systematics, or new physics? Oh, good question. If I had to vote, I mean, I don't know. It's really hard to know. I mean, I've actually read those papers very carefully. There's nothing really obviously wrong. If I had to vote, I would vote for systematics. I would vote for just something we don't know about that setup, something about this source, some kind of backgrounds. That's what I would. That's not what I would wish. I would wish for new physics, but unfortunately, I think I'm a bit pessimistic. I would guess that it's some kind of systematic, but who knows? I don't know. How well is the PM&S matrix measured? How much wiggle room do we have for it being non-unitary? I guess the PM&S. I guess I've got all the. You can see how well the parameters are measured. I believe there is wiggle room for it to be non-unitary. There's a fair amount of wiggle room. That is actually an interesting question. So yeah, so this is how well it's measured. You can see the uncertainties. Actually be interesting to make a graphic to show the size of the uncertainties. But so yeah, no, there's plenty of room to push down on the precision of the parameters to look for something weird. Yep.
Okay, so I think we can thank Kate virtually again, and I think we're off to lunch until the coffee break. And I'll see everybody then.
Okay, thank you.
Thanks. Yeah.